We're just waiting for you. Whoever you are, we're waiting for you. All right, well, without any further ado, I'd like to welcome Vanja, who's going to talk about actually two subjects very dear to my heart, malware and big data. Over to you, Vanja.
Thank you, Morten. It's great to see you. It's such a large number. I actually haven't expected such a turnout on a Friday, last session ever before the keynote. But I guess you guys are keen to listen to what Kostin has to say, so you might as well hear what we have to say here as well. So my name is Vanja. I worked for HP Security Research. I've been around the industry for some time, that you can see by the number of gray hair, or by the lack of it. So what are we going to talk about? So before we kind of dig deeper into what I wanted to present, let me give you a little bit of a concept. First, I have to admit something. So I'm a pretty lazy guy, right? So and I think it comes from my old kind of time when I was a student in school and in university. I usually had basically two phases of how I prepared my exam. The first one was, there's plenty of time, right? The second one is, it's too late already. So basically, very similar to the deadline for the VB conference. When I started working in HP, I got this small team of researchers to kind of lead, let's say, and then when I arrived, we started thinking about and working on kind of putting together some systems and processes and building this kind of a malware lab. And then we realized, as we kept receiving some samples from some of our users, that many big, like Fortune 100 companies and like even the smaller ones, are thinking and considering of building their own kind of thing. So I tried to connect like a good thing, the deadline for the VB conference and the things that we are actually working on, and I thought, why don't we write a paper which will be targeted more to smaller teams, which was our team, rather than like the overall big, huge AV labs like most of the people here in the room already have. But we had some unique, let's say, well, there were a lot of challenges, and we have also unique opportunities. And I think our biggest opportunity is that, as you probably all know, HP doesn't really have an AV product. So instead of being kind of tied to a particular technology, what you old guys have your own different malware detection languages, all the infrastructure that you develop over time, we could actually take a kind of fresh look and try to see what can we do with relatively small team and well, pretty limited budget. So, essentially, we are at the point, or we were at the point, like when many AV companies used to be. So, perhaps the talk is not going to be as much as the big data. It's going to be a little bit more about actually building a malware lab. Because by the time, like I said, by the time I submitted the paper, I was hoping we'll have all our systems in place so I can give you all sorts of idea of what's going on and all the stats and how much data we're collecting. But unfortunately, by the time I started writing the paper, the systems were not yet in place. So, and I thought, there's still plenty of time, right? And by the time that the presentation was looming, I thought we'll have plenty of data. Obviously, we have 3-4 months to put everything together, install everything. We have all the data, right? Turns out it's too late now. So, we are basically at the point of, if you remember, give you a little bit of a history as well. Some people would recognize, very few people will recognize this face. Graham Cluley, maybe. Dmitry, guys from Sophos. So this is the Sophos Labs when I actually joined Sophos Lab, right? So what you have here is there were like, I think 4 or 5 of us working in a very nice building in Oxford, and we essentially had 2 machines each running DOS, and we processed about 300 samples a month, which meant that we would get the collection, which were exchanged monthly on the first few days of the month. We would quickly run the detection, and then we would have plenty of time to enjoy after that till the end of the month. Right? So those were the good old times, and you can see some of the trays where we could use the floppy disk because we had to destroy them. It's a separate, the lab is a physically separated environment. It's isolated from the network. At the time, no internet access whatsoever. So, but it was actually pretty nice place to work at. Now it's obviously a little bit more stressful for especially people who have to work. But if you think about those small numbers, they kept increasing over time. So sometimes, I think in 99 or maybe 2000, I saw this presentation by David Chess and Steve White from IBM, who were just about to be acquired by Symantec or some of their technology, about the digital immune system. So the digital immune system is something which I consider to be like, come on guys, this is science fiction, clearly. You have some agents on the endpoints, you have some administrator tools running there, and you have information flowing two ways from the central control, like a unit, which basically analyzes malware and creates new detection, and there's the whole feedback loop between the people who are using the software and actual producer of the AV software. And so I'm fairly sure that most of the people now and most of the companies actually have a pretty similar model of working for their products. Instead of the analysis center, we have the cloud, we have automated analysis machines, we have all sorts of scanning rigs and things like that. And so that was in 2000, and I was thinking, yeah, it will never happen. But yes, indeed, it actually did happen. And if you look at the kind of, obviously we all know AV test stats, the number of malware kept growing over years, and this year it kind of stabilized. I hope that means we are doing a better job, both the vendors of the operating system and the vendors of AV, of the kind of developers of the AV product. So I think it's going to stabilize around 500 samples a day, 500,000 samples a day, of course. This is the kind of number that I was pretty ambitious when I joined HP, and that was my idea, is like, if everybody's processing those samples, then if we really want to be serious about malware research, we want to be able to have this capacity. And then, like we said, people start coming. We have our internal team that does the kind of, when I say internal, there's the internal IT team inside HP that deals with malware incidents. And so they are very much a good model customer or model of the team that would like to build a malware research facility such as like the Virus Lab. So that was like history and context. Now, the next few things I would like to cover are kind of workflow and some of the components that we need to have in a kind of successful lab. Some of the design principles and kind of recommendations that we came across during our kind of investigation, and kind of finish with a summary. Hopefully that's it. So even if when we started looking at the lab, I kind of tried to look like every single component that we need, like servers, this and that, various scanners, rigs. So I put everything on like one Visio slide. And then I realized this is a bit complicated. So I kind of went bottom up and then top down. So this is, I guess, top down, like big units, what we need to have. Like acquisition, of course, we need to get our samples somehow. We need to be able to analyze it in some kind of group. Then we need to have people who are actually going to interact with the system. So we need some kind of end-user system facility, some kind of portal. We need to have a workflow that will kind of automate everything from the process of the acquisition of the samples to the actual storage and potentially output. Of course, we need a place where to store that in the storage. And then we need some kind of auxiliary modules, which I really couldn't place in any particular category of these kind of really important parts. And then I have I have partner interfaces and feed producers, because one of the things that we do is, I think Oleg mentioned, and John, we have like a threat intelligence sharing product called Threat Central. So that's one of the things we would like to, or we wanted to incorporate in our design. So we'll kind of drill down slowly, slide by slide, into like every category. So first one is the sample acquisition. If you really, so you have really two choices. First choice is, which I thought it was the right choice at the beginning, was do everything yourself. And this is what every malware company and every AV company did. Create your own spam traps, create your own honeypots, crawlers, kind of systems, but they all require development time, they all require developers, and they all require some stability to a point. I thought that if we ourselves didn't have any malware samples or URLs that are our own, then it wouldn't be nice, it wouldn't be fair that we start and try to join the rest of the AV industry and start exchanging samples and URLs on a kind of daily basis like you all guys do. So the other possible ways is basically just, well, pay for access to some of the malware repositories, and that was the situation more or less when I joined. So. And I think it's worth mentioning with those partner feeds, there are also there are informal or formal mailing lists, and there are various mechanisms around those lists that have frameworks such as Malware Information Sharing Platform, MISP, which is used by many certs and different companies that actually exchange information about malware samples and malware incidents. It's quite an interesting framework that is open source. I think it's developed by Luxembourg cert. So after the acquisition system, clearly after we have those samples, we need to be able to analyze them. We can have various automated analysis system, both dynamic and static. So we need to make a decision on, or try to make a decision and store some data in the database. So we need to have a scanning system. We need to have like automated analysis system for like dynamic analysis, URLs, and how we analyze the URL feed as they come. We need to be able to see whether they are actually malicious or not. So we need to be able to confirm and simply not act on the flow of malware samples as they're coming in. So static analysis workflow, it typically involves anything that is done to the sample except running the sample. It doesn't involve that. So I thought, okay, so if you start to analyze as a user, you authenticate first, you upload or you get the sample somehow. The sample has to be stored to the storage, and it will just run two things. It will be scanned with anti-malware, a group of anti-malware scanners, and done some static methods such as extracting strings, the usual thing. All the checksums will be calculated. Some fuzzy checksums will be calculated. I was hoping to implement or include John's modification on Niels Himsa as well. So we had all sorts of ideas of what we can do. And then after everything is done, of course, we want to save those so we can later use it for clustering and analytics. Same with kind of dynamic analysis. We kind of start, we submit the sample, there's some pre-processing happening, we restore the analysis environment, we start monitoring. Those are the usual thing, and you guys are pretty much familiar with this, but this is just like for the reference of the people who already don't have their own lab, so just to understand what's going on. Like I said, end user systems, our team is very much, we all actually work from home. So we don't work from an office, and so we needed to have like a central facility connecting through the VPN, where we would access our research and intelligence portal, and from that portal we would be able to access all the automated systems, even the manual systems running on most likely VMware, and so we will be able to access that. So those are the important ones you need to have as well. So the big data actually, if you think about just 500,000 samples a day, I think I calculated and I wrote in a paper, maybe I miscalculated, but only for storing sample, I think you need about 17 terabytes space a year, if the average sample size is about 500K, let's say. So it's a pretty big kind of storage requirement, and that's only for the samples. So even if HP is a hardware vendor, we do have to pay for our internal hardware. We kind of have to share it with a few other teams, so we have to be pretty careful how we spend it. So in addition to that, if you think about, okay, so 500K per sample is not that big, but what about all the other data, all this kind of scanners results, rescanning results, dynamic analysis results? I think it kind of, if I understand, it gets to about 100 megabytes per file, per sample. So that's quite a large amount of data to store. We contacted one of the guys because we are also using Cuckoo sandbox, and we contacted one of the developers, and one of the guys from our team was very ambitious, and he decided that he told the developer that we're gonna most likely build a system for 5 million samples every day, and it's like, oh wait, you're a little bit too ambitious. There are some auxiliary systems we need to have. We need to have a wiki where we can store our kind of documents or internal documentation. We need our tools repository, tools that we build for our personal analysis need to be stored somewhere. They need to be controlled in source control systems. We need to have systems for authentication and access rights. We need to have systems for requesting analysis from other internal and external team. So if you think about, there are actually many boxes, and that was the kind of, eventually I didn't write or didn't put in all the links between various systems that are required. Otherwise it would be just like a mesh of systems which you couldn't be able to see. But this was the kind of image that I came first, and then I had to change and see and sort various system and boxes into like high-level groups. So and then I was thinking, like, how do I approach? What are the phases of implementation of something like this? And came across a tool that's often and frequently used in some of the kind of psychological and HR people like to use this. Like, if you don't know what to do, just put it in a pyramid or something like that. So I put it in a pyramid of a Maslow kind of a hierarchy. So you have like the most common needs to be satisfied first. So first we need to have an individual research systems, which we did more or less when I joined. Then the next level of sophistication is, okay, let's have some acquisition of samples, let's have the storage, and then let's start to share the information and including those samples. Then we should build those automated analysis systems, VM farms, all the workflow around it, because usually you have disparate systems and you need to be able to somehow connect those systems so they can work together and talk to each other. So workflow is already pretty sophisticated, I would say. And then last thing, now that you have these huge amounts of data, plug in some of the sort of HP's product. We have like a high-performance big data database called Vertica, and we also have something called Idle, which is like a search engine equivalent that allows you to store unstructured or semi-structured data such as JSON blob, and then make some prediction based on the data. So there's like a machine learning tool as well. So these are the top level, and then once we do that, we can just keep adding new stuff. So that's the whole idea. So some of the principles, and then when I kind of realized that, I wanted to kind of learn more about how we develop, what are the kind of development principles. And then I came across, I think a long time ago, I listened to a presentation from Alistair Cockburn, who was one of the kind of father of agile programming. And I thought, okay, so there's an Agile Manifesto for development. Well, is there like a one for systems engineering? And indeed, somebody from IBM created an Agile Manifesto for systems development, and then I kind of look at it and it's like, yeah, we really want to do something along those lines. So there are some principles such as there will always be changing requirements. Like when I arrived, the requirements for the labs were like pretty different than what they are at the moment. We would like to have like short development cycles because when we start building the lab together, we had to contract somebody. So they haven't reported back to us for some time. So we haven't actually closed the kind of feedback loop from the developer to us, who are the users of the system. And we just neglected it, and it kind of fizzled out. So that's very important. Researchers and developers should work together, and in most of our cases, researchers and developers are kind of mixed category because many people are one and the other. The only measure of success is something that we can demonstrate, so we can't just play with things because we can't afford that. And look, hey, this is cool, this is nice, this is this, and don't do anything. So we need to be able to push this forward all the time. And of course, like I said, it goes together with simplicity, which means like being lazy, maximize the work that you don't have to do. And then I also came across these DevOps terms, like what is this DevOps thing? And there was, somehow I started reading about it and I came across a novel, an IT novel basically. It's almost like a fairy tale of an IT manager, IT operations manager, Bill, who comes to this really badly organized IT department when you have developers not talking to guys who are in the operations, and somehow this magic character called Eric appears, right? And the Eric is like Mr. Miyagi from Karate Kid, and he kind of starts talking into this also like cryptic language that the Bill has to find out what it's all about. And basically, Eric told Bill about 3 ways of DevOps. First way, think about the systems, right? So that's very important. Do not think about any individual part of the system. Think about system in kind of the whole, because the system will be as good as the kind of worst possible part of what you have. So try to find bottlenecks and eliminate those. The second rule is amplify feedbacks. Amplify feedbacks essentially means that on every stage of development, you can deliver something, and then you get the feedback from every next stage of the development process. So the testers essentially give feedback to the developers, the users give, but that happens in frequent loops. And the third way is try to experiment all the time. Being researchers, that's not very difficult for us. So I like this principle the most, and this is where we actually were the most successful in experimentation, rather than actually having a great and big, huge lab with all data behind it. So for people who don't have a lab, I think the important points are start simple with easy wins. So don't dwell on developing all this collection system and stuff, because by not having hardware, I realized that over 5 or 6 months that it's not necessarily required. But some of the good other things is like if you start building, think about starting small, but then building up and being able to scale. I actually considered also like a fully cloud deployment of the lab, because we work remotely and it would be kind of very interesting. And as a cloud development principle is you need to expect failure, so you need to design for failure, and it's most likely that the systems will fail sooner or later, so think about that. Harness the power of community, so there are like all sorts of exchanges, there are community projects, there are free tools that we can use, as well as groups that we can join. One good example is the Yara signature group, where there's like 12,500 community Yara signatures that we can, for example, employ or deploy internally. So automate everything if you can, and that everything is source code. Basically 2 things. One is configuration, and the other one is provision. So everything can be done through tools such as Linux containers and Docker or Vagrant or something like that. It allows you to kind of experiment, and those configuration files can always be kept in the source code repository, and you can also practice kind of continuous delivery as you develop. So some of the tools that we actually ended up with, right? First one is VirusTotal. Everybody uses it. It's a VirusTotal intelligence. It allows you to find samples. It's not free. It's free when you have it, but it's a kind of, you don't have to develop any additional systems. It allows you to deploy your own Yara rules based on the results of scanning. You can get all the new samples, and it's really, really powerful, especially if you have the kind of highest level of requests and privileges. So once when you got that, we thought locally. Actually, Claudio Garnieri was here, and he developed both of the next two tools. One of them is Viper, which we'll use for local storing of the files, and it also allows you to do like really kind of great static analysis and create little projects that you can have kind of groups of files with for particular incidents and things like that. It's geared towards individual users, but we are trying to kind of extend it so everybody can use it as like in a server. It has its own Yara rules, so those are like became de facto standards in the kind of non-AV community of malware researchers. And heavily modified Cuckoo. You see there's a HP logo. I modified it. So we use Cuckoo Sandbox as well for internal development, but the Equivant fork, which basically has some additional capabilities, internal virtual machine agent hides the virtual machine better and works on 64-bit as well and 32-bit, and it has some clustering capabilities. Generally, you see all the results, which is nice. And the clustering is based on malhere project, which takes static and dynamic characteristics of the file, hashes them so that it can normalize them and finds a distance between the two files, so you can actually see which ones are pretty similar to the one that you already submitted to the system. So implementation phases, I think we more or less covered that. Start with small and then build to actually be able to get to the cloud. Implementation choices, like I said, I wanted to cloud, but we ended up with 2 racks on the right. So it's kind of exciting, but I thought I'm going to come with this kind of great architecture where everything can be horizontally scaled like this. We would have load balancers, we could have many users, but that didn't really materialize. But it's something to consider if you want to build a lab like that. So in summary, it's a pretty complex thing to build a fully functional malware lab. But you can start from something which is pretty small, and it will get you to a certain point. If you process all the relevant samples, like for example HP internally, our IT guys are doing anything between 300 and 500 samples a day, so not a lot, but it's a 300,000 big company, 300,000 people or employees in HP. So that's a kind of roughly the size of or number of files that these little teams of malware researchers inside Fortune 100 companies are looking to analyze a day. Start from small, and then I think think in terms of this DevOps ways, because it's kind of an interesting approach to development. So with that, I think we are done. I'm not sure if I have any more times, but I would like to thank you, and then if you have any questions, please do.
Well, that was kind of a blast from the past. I haven't really thought of the immune system for a while. It's been nearly 20 years. Are there any questions on this subject? We only have time for like 1 or 2, so you have to be really quick.
Any suggestions? I'm fishing for suggestions, as well. What to do or not to do.
I was actually just going to ask a very, very stupid question. I didn't quite catch the name of the data storage that you said you're using.
Viper.
That was Viper.
Yeah.
I thought you had like a data store system.
Oh, data store, the HP's data store system?
Yeah, HP's, yeah.
Yeah, it's 3-par. Yeah, it's a 3-par network storage. 3-par.
3-par, okay.
Yeah.
All right.
Vertica is a database.
Oh, okay, vertical.
It's a columnar database that kind of allows you to really
like Cassandra.
process billions of records. I mean, it's more like for querying rather than transactional, but it's kind of really pretty powerful.
Okay. So last chance, really quick. Going. Gone. In that case, help me thank him for a great presentation.
Thank you.